Today, we will bring you a new paper, a two-stage stochastic programming model of coordinated electric bus charging, scheduling for a hybrid charging scheme. This article was written by Huang. Next, I will introduce the abstract. This paper proposes a coordinated charging scheduling approach for battery electric buses in a hybrid charging scheme, i.e., both plug-in fast charging and battery swapping charging modes are incorporated in a single charging station to accommodate the uncertain battery energy consumption during bus operation. A two-stage stochastic program is formulated, where the first stage decision determines the battery inventory level of each station, and the second stage determines the charging mode and designs when, where, and how long each bus should be charged. Future uncertainties associated with energy consumption are captured by a set of possible, discrete scenarios from historical data. A progressive hedging algorithm is developed to decompose the two-stage stochastic program into sub-problems. A case study is conducted to verify the proposed models and solution algorithms. In this study, we adopt the discrete time optimization framework, which discretes the planning horizon, e.g., the operation time of the day into equal time slots of minutes. See Fig. 2. The total system charging cost is composed of two parts: 1, the electricity cost of plug-in charging, and 2, the fixed cost of the battery swapping service. In sum, the deterministic optimization model of the bus charging scheduling problem can be formulated as follows. In the real-world situation, the decision on how many fully charged batteries should be provided for the next day's operation is determined without an exact situation of the future. A common method to capture future uncertainty is to consider a set of possible scenarios. In this section, a scenario-based stochastic program is formulated, and the uncertainty associated with energy consumption is represented by a set of discrete scenarios with a given probability of occurrence. Firstly, I will introduce the experimental setup. The data is collected from 6 buses. The historical data of stock of all buses are collected for 60 days. The layout of bus services is represented by a bus corridor in Fig. 3. A service route for a bus within a day is composed of several round trips, and the charging activities only take place at the stop connecting to trips. In this study, a clustering-based scenario generation approach, namely, the multidimensional k-means method, is applied. Except for the battery-related factors, the energy consumption during a trip depends mainly on several external factors, including road gradient, air conditioning, and traffic congestion. Next, I will introduce the stochastic programming approach versus wait-and-see approach as can be inferred from the table. In the case of wait-and-see, the required amount of battery inventory no doubt increases when the energy consumption becomes higher. Another observation can be drawn from Table 3. The battery inventory is unevenly distributed among stations. Last but not least, results on the sensitivity of the solution is that one of the advantages of battery swapping is that depleted batteries can be recharged during off-peak hours with lower electricity prices. Hence, the charging cost of depleted batteries would have significant impacts on the choice of battery swapping mode in the proposed hybrid charging scheme. A sensitivity analysis on the charging cost per battery is conducted, and result